Hello everyone, my name is Yifan Wang, and today I will presenting on the topic of practical graph isomorphism. Here is the outline of today's presentation. We will start with an introduction to graph isomorphism, then move on to existing approaches, focusing on both exact and approximate methods. I will introduce the method traces and explain the related techniques like canonical labeling, the individualization refinement paradigm, search tree strategy, and finally, we will discuss the implementation strategy, and also pruning techniques. And then we will talk a little bit about automorphism detection. Let's start with the definition of graph isomorphism. An isomorphism is a bijection between the node sets of two graphs, which the bijection preserves the adjacency relationship. That is, if two vertices are connected in one graph, if and only if the corresponding vertices in the other graph be connected. This graph shows an example of graph isomorphism between two graphs, graph G and graph H. And on the right-hand side, we see the isomorphism mapping between these two graphs. That shows the function f specifies how each vertices in graph G corresponds to a vertex in graph H. Okay, if an isomorphism exists between two graphs, we say that these graphs are isomorphism. So an important note is that graph isomorphism belongs to the class NP, but it has not been proven to be the NP-complete class. There are two main categories of methods to solving graph isomorphism: exact methods and approximate methods. For exact methods, they are designed to give a definite answer, yes or no, about whether two graphs are isomorphism. These methods focus on exploring all possible mappings between vertices and then find a precise solution. They include powerful techniques like individualization refinement paradigm, which is used by the algorithm like naughty and traces. And for the traces, we will talk about it later. And this approach breaks down the graph into some simple parts. Therefore, it is relatively easy to identify the isomorphism. Another group of exact methods relies on the backtracking algorithm, like VF2 and Allman's algorithm. These algorithms explore the potential mappings of the graph vertices in a structured way, and then they will pruning the search space when solution is not possible. So in general, the exact methods are accurate, but they can be computationally intense, especially when given a large size graph. So, on the other hand, we have approximate method, which focus on providing faster but less precise solutions. These methods use heuristic or probabilistic techniques to determine whether two graphs are likely to be isomorphism. One common technique is the WR test. This test refines the graph vertices labels to distinguish non-isomorphism graph in a quick way. And although this WR test is efficient, it may fail on some complex graph structures. And for spectral methods, they often use the eigenvalues of the graph matrix, for example, the adjacency matrix. They will comparing these matrices to identify the possible isomorphism between them. And more recently, machine learning techniques are very popular. Therefore, some graph neural networks, hypergraph neural networks are developed to learn the patterns in the graph structure, and they provide a probabilistic measure to measure the similarity between the graphs. Finally, some optimization techniques like simulated annealing and genetic algorithm, they use the iterative process to refine the potential solutions. Today we will talk about the traces algorithm. The traces use the individualization refinement paradigm combined with a search tree to explore the graph isomorphism. And unlike the traditional individualization refinement algorithm like Naughty, they didn't use the DFS strategy. They used the BFS strategy. We will talk about later. Okay. So before introducing the algorithm, we will start with some preliminaries. So first is graph coloring. Graph coloring plays an important role in traces to refine the graph when refining the graph partitions. So a coloring of a node set and a graph is a surjective function from a node set to some integers. And the number of these colors is denoted by pi. And we denote a cell of a coloring is the set of vertices with some given color or with some given integers. A discrete coloring is a coloring in which each cell is single. That means this cell contains only one node, and the total size of this partition is equal to the number of nodes n. Sometimes we also use partition to denote the coloring. I will use both of them in the following slides. So in I want to introduce the graph actions and isomorphisms. In graph theory and in the context of the graph isomorphism, we use group actions to describe how we can transform the vertices of a graph that preserve its structure. So more specifically, let the symmetric group denoted as Sn and the act on a set it denotes the act on a set of the vertices in the graph. So the symmetric group consists of all possible permutations of the vertices in the graph. So when we apply permutation from the symmetric group to a graph vertices, we produce a new arrangement, new coloring, new partition. But the key here is that these transformations do not change the connectivities to the graph itself. So this is important because finding an isomorphism between two graphs is essentially involves finding a permutation of the nodes that makes the graph identical. And also here are some notations. For any node and permutation from the symmetric group, we use VG to denote the image of the node V under the permutation G. And we use the same method to denote other objects. For example, any set of nodes, a graph, a partition, or a colored graph. Now we are ready to move to the canonical labeling. So canonical labeling is a function that transforms a graph into a unique form that remains invariant under the isomorphism. This means that if two graphs are isomorphism, their canonical forms will be identical. By converting graphs to their canonical forms, we reduce the isomorphism problem to a very straightforward comparison of those canonical forms. And tracing is a method to find the canonical forms of the given graph. Note that such function, canonical labeling function, need to satisfy the following two conditions. That is, for any G and coloring pi, the output coloring graph should be isomorphism to the given graph. The second one is the canonical form of the given coloring graph should be equal to the canonical form of any permutation of the given coloring graph. So the challenge lies in finding this unique labeling, and that lies in finding such unique representation and labeling, and that's where we need the search tree. The search tree is a structured way to explore all possible such labeling of a graph. So the traces constructs a search tree where each node represents a sequence of vertices, and the root is an empty sequence. As we move down the tree, the sequence becomes longer, and each leaf of the tree corresponds to a discrete coloring. And also at each level of the tree, we make decisions about how to label or individualize a specific vertex in the graph. As we move down the tree, we refine this labeling by further fix or individualize such vertices and analyzing their connections between different cells. So the deeper we go, the more details we will understand about the graph structure. And then we will introduce the individualization refinement. This is a central technique to traces. So for the individualization, it involves fixing specific vertices to break the graph symmetry. And by choosing and fixing one node, the algorithm reduces the number of possible permutations to consider, which will make the whole process more easier to distinguish between different graphs. Here is a formal definition of individualization. It is a function that outputs a new coloring, a new partition. And this process is like once the vertex is chosen, in our context, its label will add by 1. And for the nodes in the cells that the label is larger than our selected vertex, their label will also increase by 1. And then the refine, I will introduce the refinement process. This process partitions the nodes into equivalence classes based on their connectivities. So after individualizing the vertices that share the same structural properties, for example, have the same number of connections to other vertices in the same cell of the given partition. So they will group these nodes with same structural properties will be grouped into the same class. So this process, the process of refinement will continues until it is stabilized, meaning that the further partition is not possible, which means we will have an equatable partition. The meaning of equatable partition is that for any two vertices in the same cell of the partition, the number of neighbors they have in any other cell must be the same. So here is the formal definition of the refinement. A refinement is a function that outputs an equatable partition. It will take a colored graph and a sequence of nodes as the input. For the node in the sequence, itself must be one cell in the returned partition. And also, this function is invariant for any permutation. This is the refinement algorithm used in the traces. It will loop through all cells and check its connectivity with other cells. The other cells will be separated based on the patterns they have from the from the cells they are focused. And specifically, the overall refinement function is implemented by a recursive way. So it ensures that the vertices with similar structure properties are grouped together. So this step-by-step refinement is crucial for accurately identify the structure, isomorphism structure in the graph. It will start from the root node, and then when we go deep to the tree, it will each step will add one node, one individualized node. So in the search tree, the target cell selector also plays an important role in determining which node to explore next in the next layer. So the traces prefers to choose the largest non-single cell, which will keep the tree shallow. So note that the target cell selector needs to have three properties. It is a function, and it will return a node set. And this function is also invariant for any permutations. So for um, such tree strategy, using the induction and the properties of the search tree, the properties of refinement function and target selector, and also the individualization function, we have the following important lemma. This lemma says, for any partition and permutation on the given graph, their tree must be same. It means if the two graphs are isomorphism, they will have the same tree. So now we describe how the search tree can be used to compute the canonical form. In traces, canonical labeling is achieved by using a node invariant function. This function determines the canonical form of the graph, and it will ensure that the form is both consistent and unique across the isomorphism graphs. This is a formal definition of this function, and the output is some ordered set. So the node invariant is computed for each node in the search tree, and importantly, it is also invariant to any permutations. So to define the canonical form, we first find the maximum node invariant value among all the leaves in the search tree, and we use the corresponding coloring. We will find the canonical form of the and then find the canonical form of the given color graph. So the reason this approach works is that the node invariant function transforms a problem of finding isomorphisms into a problem that comparing these labels in the leaves. So by making sure that the environment labels are consistent for all vertices across all the isomorphism graphs, we can guarantee that the canonical form is also consistent. So here are some formal reasons. So the returned form, we need to show that the returned form by the canonical labeling process we talked before satisfies the properties of the canonical form. So first, the considered canonical form is selected from the leaves in the search tree. So based on the definition of such tree, each leaf represents a discrete partition of the graph. Then its corresponding quotation graph, that is the which is the candidate canonical form, is an isomorphism to itself based on the property. So therefore, the returned canonical form must satisfy the property C1. For C2, from lemma 1, we have the following relationship, which is exactly the property of C2. So the implementation of traces involves strategy for pruning and search tree, pruning the search tree using target cell selector and the node environment. So one of the primary goal of pruning is to find the symmetries in the graph. So symmetries are cases where different partition over the vertices will have the same graph structure. So when the algorithm detects a particular vertex node's coloring, it's just a reordering of another already explored arrangement. It prunes the branch of the search tree because it doesn't provide any new information. So the node environment function assigns unique labels for vertices based on their structural properties. So during the refinement process, if the environment labels suggest that two vertices are structurally different, then the algorithm will immediately stop exploring that branch. So this means that if the current partition labeling doesn't align with the node environments required for an isomorphism, the algorithm will cut this path, and it will saving the computation time. Specifically, we have the following two pruning rules. So for nodes in the same level, if one node has a smaller node environment than another, it will remove this node and remove this path. And for the node in the same level, if their node environment are not same, and the node will also be ignored. So the choice regarding the target selector, so the choice of target cell selector has a big effect on the shape of the search tree. Traces prefers to select the largest non-single cell as the target because they following the BFF strategy. They want to break the symmetry of the graph very quickly. So by focusing on the cells that have the most potential to break the symmetries, the algorithm will cut more. The algorithm will cut more branch, and it will save a lot of time. So during the refinement phase, quotient graphs are used to represent how different vertex graph related to each other. So a quotient graph is generated by an equitable coloring. So if such graph structure at the given level of the search tree fails to match the expected structure, that branch will also be pruned. In traces, the node environment use the sequence of the quotation graphs. And when using such graph, it will satisfy the three properties which defined in the node environment function. And then here is an example of the process for constructing the search tree. They will start from the central graph, and then you will find the target cell. After individualization, in the next layer, the nodes indicate an equitable partition after the refining. And we will move further down to the tree. And finally, at the leaf nodes, in the bottom at the leaf node, we reach a point where the graph vertices have been fully individualized and refined. So these leaf nodes represent the candidate canonical form for the graph. So we can also obtain the automorphism group. So automorphisms in a graph are mapping from the graph onto itself that preserves its structure. So for any leaf in the search tree, we have automorphism group defined as this formula. And from this formula, we found that detecting the group, automorphism group will help us to cut the search tree more effectively. And therefore, we will have the third pruning rule, that is for any permutation, for the node that is deeper in the graph, in the search tree, if they if if they are deeper, if so for the deeper nodes, if they have the same image after the permutation, then the algorithm will prune this node, will remove this, and also will remove this branch. Okay, that is all about today's presentation. Thank you for listening.